Ladies and gentlemen, my name is Krzysztof Turzyński and I have a pleasure of chairing this session. This session is very short, so this is not a very big job for me. The big job is for the speaker, Narendra Sahu. And because we are in a gravitational waves workshop, everything is gravitational waves related. Also, leptogenesis and dark matter. And let's see how.
Thank you, thank you. So it's the main focus of this talk is not the gravitational waves later, but leptogenesis and dark matter. What else? Since it is related to gravitational waves, somehow we have to say a few words about the gravitational waves. So, can you hear me? Okay. Okay, let's go ahead. So the title seems there is a thermal leptogenesis. I will discuss a bit kind of the leptogenesis part, and then I will see that how it is connected to the dark matter and the gravitational waves in a canonical seesaw scenario. And okay, so before going to that, we should talk about the standard model, and we know that now we have a standard model is a successful theory for elementary particles that we know, but still we know that the standard model is not enough. We need new physics because of some reasons, and the reasons are few of them are noted down here, so like non-zero neutrino mass, and then baryon asymmetry of the universe, and also the dark matter, and also the gravitational wave. So I have not noted down, but it is also one more motivations. So these are the various things that led us to kind of go beyond the standard model scenario. And so since I want to discuss more about the leptogenesis, I will just go through the history of the leptogenesis quickly before coming back to the main motivation of this paper. And so, okay, so this is kind of the neutrino mass. The neutrino mass, we know that that the standard oscillation experiment tells us that the neutrino has sub-eV masses. And so, but we don't know the neutrino can be either Dirac or Majorana. So Dirac means like the lepton number is exactly conserved, but if the Majorana, then the lepton number is violated by 2 units. However, if you want to consider like the Majorana, there is an advantage that we already have a dimension 5 operator within the standard model, and therefore you can easily construct a dimension 5 operator to get the Majorana mass of the neutrino. And so long back people have been working on this case and seesaw mechanism, one of the kind of BSM scenario where you can integrate the heavy particles and then you can get back to the same dimension 5 operator. There are 3 ways you can extend the standard model. So one of the cases is like the type 1 seesaw, so the name called the type 1, where you have to extend the standard model with right-handed 3 right-handed neutrinos. And then in case of the second case, like the type 2, where you have the standard model can be extended with the scalar triplet, or you can have a type 3 scenario where the standard model can be extended with a triplet fermions, hypercharged zero triplet fermions. But in all cases, you can integrate them and to get back to the same dimension 5 operator. And so it is nice. And people have been explored quite significantly since 1970s. And a more advantage of this considering this the Majorana mass of the neutrino is that it can also give you like the baryon asymmetry via the leptogenesis route, and because of the kind of the Sakharov criteria which was pointed out in 1967, and it has what it says that it has if you have V violation or L violations in a theory, and then also on top of that C and CP violation, but CPT is conserved. And all the processes you are considering in a thermal bath, they have to satisfy the out of thermal equilibrium conditions. Then you can produce some reasonable lepton asymmetry, and then baryon asymmetry of the universe can be satisfied. So this is also kind of correct, related to your non-zero neutrino mass of the theory. And so why this is? Because basically within the standard model you cannot have very enough CP violation that can give rise to various leptogenesis. But on the other hand, these gentlemen who showed that at kind of there are some kind of non-productive processes which can violate B plus L within the standard model, and that can give you lepton asymmetry in a processes or the baryon number violation, such kind of process called the spiralons. And the spiralons are basically some non-perturbative processes which is they're separate at the zero temperature, but at a high temperature, when you consider the temperature larger than the F value, the free energy in the standard model. So basically, that will give you the unsuppressed baryon number violation, and you can have baryon number, lepton number if you can have baryogenesis. But within the standard model, although this ingredient is there, but we don't have enough CP violations. So another gentleman, these two gentlemen like Fukuyama and Anagida, so around 1906, they thought about that kind of considering extending the standard model in the type 1 CISO scenario, and then they saw that the CP violating out of equilibrium decay of the right-handed neutrino can give rise to the adequate CP asymmetry, and that can give you the correct lepton asymmetry, and then through the spiralan transition, as I showed in the previous page, that can give you like the correct baryon asymmetry. And the amount of through the spiralan amount of the baryon asymmetry cooked can be calculated by easily in this way through the chemical potentials the particles which are in thermal equilibrium, and some people put earlier around 1988, around 1990s, these were the people who calculated that. Good. So now the question is afterwards, like many people that started correctly producing by writing down the correct Boltzmann equations, and then they found out the decay of the right-handed neutrino can correctly produce the lepton asymmetry. And in fact, one important parameters like here, the important parameters are the decay, all this decay, scattering, and the washout process also included here. And many people, there are very few papers are early papers are mentioned here, but there are kind of hundreds papers at least people have worked out in this direction, including our chairman. And so the one of the important parameter is like the K, so which is like the kind of defined like M1 tilde by M star, and this M star is like something kind of fixed value. And then if K has to be like the smaller than M star or the larger than M star, the K, yeah, so that then it can have like the weak washout regime or the strong washout regimes. And in fact, in both cases, these are the people early, sometimes these people shows that this is one of the paper, but there are so many people have shown that in both cases, whether it's the strong washout regime, which is K is much larger than 1, or in the weak washout regime, K is much less than 1, both possible to generate the correct lepton asymmetry. And so people also quantified in this case also that, so people have shown that there could be an upper bound on the CP asymmetry in this case. And by taking this is the easiest way to show that by using this so-called Kasa-Saibara parameterizations. And you can find out using this parameterization, you can show that there is an upper bound on the CP asymmetry, which is proportional to the right-handed neutrino mass and also the light neutrino mass is M3. But the question is, the moment you put like this kind of the upper bound, so there will be also some kind of, there is a lower bound on the right. This turns out to be a lower bound on the right-handed neutrino mass, which comes out to be order of 10 to the power 9 GeV. And so the question was like, so when to generate this right-handed neutrino, and if you believe like the standard Big Bang cosmology, where the universe has gone through an early inflation period, and after that it has to be a reheat temperature the universe has gone through a reheat temperature to produce these particles, then the reheat temperature has to be quite at least 10 to the power order 9 GeV, and that's quite high. And so in this case, people have to find out many other alternatives. There are so many alternatives, and to bring down the leptogenesis scale to kind of at least a PeV scale. And some of the things I also tried with Ernest Ma, with Paul Sarkar. Now, so giving all this background, now coming back to my talk. So the main motivation here is, I'll talk about this paper. So one motivation of this paper is some kind of, as I said, we have leptogenesis in the canonical CISO scenario, as well as, and which is related to the dark matter and the gravitational wave. And pictorially, I have shown it here. Let's say the standard model is extended with like your the three right-handed neutrino N1, N2, and N3. And then in this case, your N2, N3, I could let's say assume that this N1 is and impose a G2 prime symmetry under which this N1 is odd, so I put it in this box. But this N2 and N3 are even, so I put it in this box so that they can have coupling with the standard model particles. But also I want another singlet formula like S and a singlet scalar rho, so that I want to have a low scale leptogenesis through the decay for S. And so what is basically, I put them some kind of another box which by imposing another G2 symmetry under which this S rho are odd and all these particles are even. And so similarly, these two particles are basically representing a dark sector, so they will be like your odd under a G2 prime symmetry, but all other particles are even. So in this case, so this N2 and N3 couple with the like usual lepton and Higgs doublet coupling, and so that they will generate the neutrino mass. Okay, but this N1 is not there, so at least two of the at least the two neutrino mass we can get it from here in this scenario. And then, so when rho will get a wave in the high scales, so it will do the two things. One is it will provide a mixing between S and N2 and N3, and so that it can, the SDK can, at the late time, SDK will produce the lepton asymmetry. But the rho is kind of breaking the G2 symmetry spontaneously, so therefore it can lead to some kind of G2 symmetry breaking, and that G2 symmetry breaking can lead to some kind of domain wall, for the production of the domain walls. And so the dynamics of the domain walls can generate kind of the late in the, once the domain wall disappears in the late epoch, so they can produce the gravitational waves. So that's the way it is related in this case. And so now I'll come back to whatever I said here pictorially. I'll come back, go one by one case in the details. Okay, so having said this, you can write down a Lagrangian. So it's based on these three particles, like a standard model with N1, N2, N3. And the relevant Lagrangian, you can say that here you have a kinetic term, and the most important part is like the interaction between your N rho S. This N is basically your N2 and N3. So this coupling is a bit larger, or we have to keep it larger so that S can come to the thermal equilibrium to give rise to thermal leptogenesis. And the other part is the scalar potential here is like you have the Higgs, the standard model Higgs doublet, supposed to be square here. And then also there is a rho, okay? So this is the usual kind of the Lagrangian that we will use for the further purpose. Now coming back to the one by one that I said, the first I will go back to the standard, the neutrino mass. How can I generate the neutrino mass in this case? The neutrino mass is basically you will have the usual neutrino, and then you have a N2, N3, and then you can have the S. So you can have this kind of the mass matrix for your for all the neutral fermions. And so if you make the diagonalizations of this part, then where this basically your MD is, we are calling like Y scope, sorry. So this is the MD part here is coming from the MD part, and then this part is the D part is coming from the rho have. So when the rho gets a vacuum expectation value, so basically it is producing some kind of mixing between S and N, and that is given by your D terms. And then Mn is the mass of the Marana mass of the heavy right-hander neutrino. Ms is the mass of the heavy S, which is lighter than N. And then this part is the 0, which is light neutral, of course. Then when you diagonalize, you can produce your masses. So these are the masses, is basically the heavy neutrino masses are like this, which is a small admixture of kind of small mixings with the S. And then your Ms prime, which is kind of, so if your D is very, very small, basically you will go back again to the same Mn and Ms, okay? And the mixing angle between your Mn and Ms is basically D by Mn minus Ms. So this D is basically proportional to the vacuum expectation value of the rho. So the neutrino mass is now, once you get like Mn, Mn prime, so you can get the correct neutrino mass, light neutrino mass in this way. And this is basically when D goes to 0, you will get back to the very usual type 1 seesaw light neutrino mass. Okay, so far so good. So I explained you, as I said, first the neutrino mass part. Now I will go back to the leptogenesis part in this case. So as I said, so you can have, so we are talking about the thermal leptogenesis. That means this n has to be like the s, which we are saying that the decay of the s is the s is kind of the lightest particle among this n2 and n3. n1 is basically the odd sector particle, the odd sector particle. So it is not contributing anything to the leptogenesis. It is representing the dark matter. So this S is lighter than N2. When a rho gets a wave, S mixes with N2 and N3. So let's say S is dominantly mixing with N2 and then S can decay at the late time. But so before that, because of this rho, N2 has a rho S coupling, so it has a rho S can go to like the thermal equilibrium. So these are the processes, which is basically delta L equal to 0 process, delta equal to 1 process. Similarly, I have not noted down the delta L equal to process also there. But so this is the diagram which is not suppressed because there is no mixing between happens like so this directly S can come to like the thermal equilibriums through this exchange of the N. So therefore, S can be, I will show you that later, the S can be brought to thermal equilibriums. Now, so if it comes to thermal equilibriums, how it will decay? So it can only decay through like you are mixing between S and N. So when a rho gets a wave, and so this will happens. Oh, okay. So it's basically S will mix with like N2 and then N2 will decay to like L and H. So that is the way. But before that, I will show you that how it, whether it is coming a typical case, we have solved that the Boltzmann equation to show that the S is coming to thermal equilibrium or not. And so this typically depends on your this Y and S coupling. So this is the coupling. Yeah, this is the coupling is basically most crucial point, which is decides the S has to come to thermal equilibrium or not. Okay, so this implies that, so this basically we have taken two values and you can see that they are appropriately by choosing your YNS coupling. So basically you can bring S to thermal equilibrium. So S can give rise lepton asymmetry while it decays. Okay, so how it will be do? So when S is mixing, when D gets a wave, there is S mixing with the N2 and then N2 decay to LH. So that we will have the finally, so we assume that there is a hierarchical mass between N2, N3 and S, so that any asymmetry produced by N2, N3 earlier, so that is erased. And then the final asymmetry is basically produced by your SDK through this. So the more, but then you see that, basically when the S is decaying, it is not suppressed, the CP asymmetry is not suppressed because it is equally cancelled from the numerator, the D part is cancelling between from the numerator and the denominator. So that is most kind of, okay, we took this advantage, but then the decay parameters, which is like here sitting it here, so that is because of that's theta mixing, so it is the decay parameter is suppressed, and it is proportional to your mixing angle square times your the mass of that S. Now you see that the main argument here we are trying to see, usually in the thermal leptogenesis, what is I was saying that the Davidson-Ivara bound tells you that your right-handed neutrino mass to be quite heavy, like 10 to the power 9 GeV, and then we are trying to do this exercise, whether due to this gamma is proportional to some kind of mixing angle squares, whether due to this, whether we can decrease the mass scale of the S, so that it can give you the correct lepton asymmetry or not. That means whether we can realize a low scale lepton asymmetry. This is the most crucial point. But then we also realize that there is a CP asymmetry also proportional to the mass of MS. So if you reduce the mass scale of MS here to realize the low scale leptogenesis, the CP asymmetry is also proportional to mass, so that will be also reduced. So this will be like contrasting each other. Like one way, you want to reduce the scale of MS to realize a low scale leptogenesis. But at the same time, when you reduce it, the CP asymmetry also reduced exactly like that amount, and then it will not give you the correct lepton asymmetry. So there is a puzzle between here these two parts, and whether how much we have to reduce the scale of the MS, and we have to do it. So we have to solve the Boltzmann equations, and that's what we did this exercise. And then what we did is that few benchmark points we tried to depict it here, and whether we can produce lepton asymmetry or not. So one typical point, let's say you are the benchmark point 1, you say that, and here we didn't produce the correct lepton asymmetry because of this particular choice. If you look at here, the mass of the MS is like, let's say, 10 to the power 7 GeV, 6 into 10 to the power 7 GeV, which is much, much less than your 10 to the power 9 GeV, at least 2 orders of magnitudes. But then it doesn't produce the correct lepton asymmetry because of when you reduce the mass scale MS so much, your CP asymmetry is also reduced accordingly. So you can produce the correct, we didn't produce the correct lepton asymmetry. And this is the correct. And on the other hand, if you consider like the other 3 benchmark points like a BP2, BP3, BP4, we can produce the correct lepton asymmetry. Let us look at the BP2 here, and we see that we can correctly produce the lepton asymmetry by choosing appropriate parameters. Basically, in this case, we have taken that the mixing angles to be like your 7 into 10 to the power minus 3, and here for benchmark 3, 10 to the power minus 5, here it is 10 to the power minus 4. So what is achieving basically here within for all these parameters, the mixings, S is coming to thermal equilibrium, but in this case, the washout effect is a bit less. In this case, washout effect is large. And also the other part is the mass is too low that it is not giving the enough CPS. Okay, so this is a one demonstration for that through the BP2 where you see that it is coming to the equilibriums and and also producing simultaneously the correct lepton asymmetry. This is BP3 again. It is because of the small say mixing, so it is going out of the equilibrium very early and then decay at the late time, and by that time there is no washout effect, so directly it will producing the asymmetry. And similarly, 4 also exactly the similar way. It is also a similar, very similar to like BP3. It is also going out of equilibrium very early and decay late, and when it is decays, there is no washout happening, and so it is finally producing the correct asymmetry. Okay, so the summary has to be given here. So we gave the summary here. Basically, we are trying to find out whether how much we can give by. So this is like the MS, and this is like your. We put like the epsilon s k time your some kind of the maximum value we put, and this is kind of the correct lepton asymmetry. These lines. And so below this part you cannot produce because it is for this part you cannot produce the correct lepton asymmetry, so because the CP asymmetry is very low. And this part you can choose appropriately the case so that you can get the correct lepton asymmetries. Okay. And theoretically this part is not accessible because the same way like there is a bound lower bound, so your CP asymmetry is proportional to the mass. So therefore, so this line there will be no point we can have in this part. So basically all points are produced in the side and this part is not producing enough asymmetry. This is exactly, and this part is basically you are appropriately choosing K, you can bring them to the correct lepton asymmetry. So these are the valid region. Okay, so I said so many. The summary is like here. Initially, I was saying that whether we can produce the, we can bring down the scale of mass ms in comparison to the mn or not. And if you look at this point, this is hardly is basically something like 4 into 2, 3. So few times here 10 to the power 8 GeV. So you cannot go so arbitrarily so small and to give rise kind of the correct lepton asymmetry. Okay, so this is the summary, and now we have to go to the other part of the story, which I was talking about the gravitational waves, how it is generated. As I said in the beginning, so the rho is playing the major role here, which is simultaneously was giving the mixing between S and N2. And also when the rho gets a wave, there are also kind of a discrete symmetry G2 symmetry prime is breaking. And the breaking of, we know that when the discrete symmetry breaks, the gravitational waves can be produced. And there are lots of work has been done in this direction. So I will refer to this one of the kind of the review work, what all these papers are cited in that paper. So basically, you can parameterize a domain wall in this way. This is called the profile, domain wall profile, the hyperbolic, 10 hyperbolic proportion. It's rho z is, you say that it is like the z directions only, and then it is proportional to the v rho, times 10 hyperbolic alpha z. And so when it is basically z goes to the infinity, it is rho z is basically proportional to plus minus. It goes from minus to 0 to plus 0. Okay, so these are the two vacuums. And then you can calculate the surface energy density of the domain wall in this case, which is proportional to the V rho square. That is kind of most important part. And that is most important parameter of a domain wall. These are all topological defects. I think there are talks today you have heard. Now the question is, if you have domain walls, then you can usually when there are domain walls there, they will stabilize, and unless you have a bias between the two sided of and two vacuums. So therefore, most of the time, or this is a common law in the literature, is that you have to somehow create a bias between the two vacuums so that the wall can so that wall can disappear. Okay, and so this can be done by hand. This is what here we put by hand. This is like a bias term, which is proportional to some kind of the linear term of the scalar rho. So which is, and that is basically it is proportional to the V rho. So once you have a linear term introduced into the potentials, so then you can create a bias between the two vacuums, minus V rho and plus V rho, and then you can see that earlier it is basically 0, but now you can have a mismatch between the two vacuums, and that mismatch can be calculated like this much. And there is a small constraint on this bias term, and the bias term has to be large enough so that the wall has to disappear through the collisions before the BBN epoch. And so this gives you some kind of your annihilation, T annihilation, time of annihilation is something like the proportional to the sigma, like the V bias. And so this gives you some kind of a breaking parameter, this mean V larger than this, which is V rho is proportional to something about like 10 to the power 5 TeV by putting M rho equal to 1 TeV. Now, so that also the another thing is that the domain wall has to also disappear before they could start dominating the energy density. So that is also some kind of T annihilation has to be less than T domination. That is also inversely proportional to sigma. So they are going in the two opposite way. So the T annihilation has to be less than T VBN, and the T annihilation also has to be some kind of before all the domain wall has to annihilate before that dominate the energy density of the universe. So this way we can find out something like the annihilation temperature, okay, and that is basically it is proportional to the V rho, okay, and that is the most important parameter in this kind of case to calculate the gravitational wave spectrum, and this spectrum is basically is proportional to the annihilation temperature, and so and also to the sigma, okay. And so one can easily calculate this the peak frequency. So particularly I will show you how the spectrum look like later, but here you basically you can see that what you assume is that due to the collision of these domain walls at some point at a particular point T annihilation that disappears, and that's why it will give you some kind of the peak, like the frequency a peak is proportional to some kind of the annihilation temperature. And if you put a conservative bound here, so you will get some kind of, so if you put a conservative bound, something like here 10 to the power minus 2 GeV, so you can get something like around 10 to the power minus 10 Hertz, and with the appropriate other parameters. Okay, so basically you can, the amplitudes when you calculate, so it is basically the peak amplitude multiplied by this part, the multiplied with the frequency, and that is part is like if f is larger than f peak, so this is the dependence is like this, and if f is less than f here f peaks, like here, so if it is like f peak and then f less than f peak and f larger than f peak, so this is what it looks. And so this feature is this domain wall, that the gravitational wave generated from a domain wall is a typical feature like these triangular features. And so one can, so there is, and one of the most important parameter for the domain wall, the gravitational wave coming from the domain wall is basically the sigma. That is the energy density of the energy density, which is related to the phase transitions, the rho. And so that is basically you can have omega gravitational wave square at the peak times, these things. And some particularly by taking few parameters here, if you look at it, so this is one of the parameters which is coming to like your EPTA range, and this is like your the 1 point, so which is like the annihilation temperature, conservative we take 10.3 GeV, and sigma is like something like 7.5 into 10 to the 8 EV cube. And then, and for the BP2, which is like this one, which is like annihilation 0.5 GeV, and then if you, for like the annihilation temperature a bit large, then you can have also the larger frequency. So the frequency is basically depends on your how high is your annihilation temperature, and so depending on your annihilation, if the annihilation temperature is small, so your frequency is small, so you can prove these regimes. On the other hand, if you have the annihilation temperature is a bit large, so you can have the frequency, you can get large frequency. Okay, so coming back to now towards the end. So basically, we are trying to give you some kind of a relation between that the expectation value of the rho and the annihilation temperature. So these are related because this the vacuum expectation value of the rho, which is giving rise to the domain wall. And so that is also give you some kind of the mixing between your mixing between the S and N2 that give you leptogenesis. If I go back earlier, so these are the two parameters, that is the BP1, and these are the two BP1 and BP2 sitting here. Okay, so that gives you like the correct, simultaneously explain you correct lepton asymmetry, and you can generate the correct gravitational waves, some gravitational wave spectrums. Okay, so now coming back to the summary plot here is basically, if you go back to like in this part, it will have a large V-rho will give you kind of a large domain wall dominations, and so it is discarded here. And of course, this is kind of this part, you have a small annihilation temperature is excluded because that will also by the BVN. And then if you go back to go towards the these are the range which is of course is allowed, and then what we try to give is that we just taken some of the points from the various experiments, and then the projections. Basically, these projections we put it inside in the plane of the V-rho versus the annihilation temperatures. Okay, so these are all these points are shown in this plane, and so one can have through access these points through the domain in these regimes, and which are allowed through or allowed to prove these scenarios. And okay, now I finished this part, so I will come back to this the dark matter part. As I said in the beginning, if you remember, the dark matter part in this pictorial I have shown you here, this N1, which are the one of the right-handed neutrino is odd on these prime symmetries. And so that is like the behaving like dark matter. But if you consider like only a singlet, then below 1000 GeV, the mass of the singlet is usually overproduced. On the other hand, if you consider like a doublet only, so then it is also below 1000 GeV, they are underproduced because of the gauge coupling. And what I try to show you here is that if you appropriately mix between a singlet and the doublet, then it can give you the correct dark matter. And that is what I will show you in the last part. Okay, so exactly the Lagrangian is given here for the singlet doublet dark, so-called singlet doublet vector-like fermion dark matter. And this is the singlet part and the doublet part. And then there is a mixing between the singlet doublet like your psi Hn and through this Majorana mass. Okay. And so basically what you do is, well, due to the mixing between you can have a 3x3 mass matrix, and you can have a 3 states, 2 states coming from the doublet, like your psi 0, it is a vector-like fermion. So you have a L and R, and there will be a NR. And so you have a 3 states, and then if you diagonalize 3x3 mass matrix, you can get 3 states, and then which you will get the lightest one will behave like the dark matter, and these are the 2 heavy states. And of course, on top of that, there are also the psi plus minus coming from the charged part. So that is also there. So you will have 3 neutral states. One is a kind of dominantly a singlet part, which is m cos Yeah, this is the dominantly singlet. So this is MR1. So this is the dominantly singlet, and this is the dominantly the doublet, and that is of course this is only the doublet one. And on top of that, there are also the charge partner. But anyway, I will, since time is getting finished, so I am showing you that. So the mixing between your these two part is basically the singlet and doublet mixing can be given by this way. And then the summary I am trying to show you here is in this plane of the dark matter mass splitting between the singlet and the doublet, and then how much is the mixing, which is in terms of the sine theta. And if you try to find out the correct Rayleigh density in this plane of the mass of dark matter versus the delta m, so it is basically, it will give you, this is the regime where you have underabundant, this is like the regime where you have overabundant, and these are the points which satisfy the correct Rayleigh density depending on the mixing angle between all the way 10 to the power minus 3 to something 0.5 or so. But all these points are not allowed by the direct detections. So all these are ruled out. So only finally you can have some of the points which is on this part. These are allowed by the direct detections. And so that's it. Yeah, I think I am in time. Thank you.
Well, let's see. All right, thank you very much. And now we have time for questions. As a chair, being pleased that somebody remembers my papers from my PhD period, I will try to ask my first question. So you have a mechanism of mixing this S field with the usual neutrinos, and if I understand correctly, this gives you a chance of making the lightest states participating in leptogenesis decay later that it would normally have in the standard leptogenesis scenario. So you've got more control over the process, and you can control the strength of the washout processes.
Right. Yeah.
All right. So are there any questions from the audience? So while you're thinking, I'll ask my second question. So you showed us a couple of benchmark points, and this BP3 in terms of the mass of the S state and the mass of the second to heaviest neutrino features more prominently than other benchmark points, also in terms of generating the gravitational wave signal. So, I mean, is there any...
No. The gravitational wave part is, the gravitational wave part, the two benchmark point is not the same benchmark as the leptogenesis benchmark.
Yes.
The gravitational wave, so if you look at here, this 1, 2, this is not the same as like the 1, 2 there.
No, because number 1 and number 2 have the same masses as BP3, right?
You mean this one?
Yeah.
Yeah, this one is this was the BP3, yes.
Yeah, so this is BP3, and this is the scheme which is present in BPGW1.
The gravity, yes, right. Yeah, correct.
Okay, so and this is the one that's special about the delayed decay.
The delayed decay, yes.
Okay. All right, guys. Any further questions?
I have hello. Yeah, I have a question. Like this kind of mechanism always generate this 5 gravitational wave spectral behavior is goes to 5 cube and then come back to 1 over 5 f. Sorry, 5 f to the cube and then go to a peak. Then after that, this always goes 1 over f. Is this spectral behavior is always the same for all mechanisms?
Yeah. So this is specific to the domain wall, a kind of yes. So this is specific to this topological defect, yes.
Okay, so the follow-up things that current observation from NANO-Grav, they typically predict base treated value.
The low frequency kind of.
Yes, this goes f square, nearly f square type GW behavior, the base fitted value. Is this kind of scenario can be fitted with this NANO-Grav signal? Any
okay, so as I said, sorry. Yes, we also tried, sorry, this one. See, if you look at here, this particularly, I mean, you adjust these parameters, you can reach up to this part.
Yeah, amplitude can be reached, but the spectral behavior,
you cannot
match with this the current observation.
You cannot fully match. Yes.
So
because these are the typical features you can see. Otherwise, you cannot. I mean, suppose for example, if you take cosmic string or domain walls, they have a typical features rather than the full fitting of the gravitation. For example, let's say we are trying to fit this value. Okay, now by taking only this the tips. Okay, we try to see only what are the range of this EPTA. Now this one. So this will be like some kind of this parameter. In this parameter range, you can have this particular point on that, only the tip point. Okay, but I mean, if you want to try to fit other points also, then you will have some parameters in this plane. I mean, this some T annihilation and some V rho you have to take to fit like one point in the EPTA. So this is considered like one point in that plane.